Okay, I am back. This is part two of the KT Extinction event talk. I left off right here, basically summarizing that probably dual causes as to why this extinction event occurred. The Deccan Traps result of the Indian subcontinent moving over the Reunion hotspot, which I'm going to explain very soon here. Um, Erupted massive amounts of lava, enough to cover the United States and 200 meters thick in under a million years. So this just had catastrophic. I won't say catastrophic, but it definitely affected the climate by rapid cooling and then a heating and then a rapid cooling and heating every time this thing decided to really pop off, um, thus putting stress on life forms. And then sort of a third of the way through this thing, a 6 mile piece of rock decides to come and whack the earth, and really that's just what you didn't need at the time. And of course this has just dire effects on the planet. Okay, continuing on. The setup prior to the event. Okay, so we have massive rifting or lava outpouring associated with the breakup of the supercontinent of Pangaea in the Triassic. This caused the climate to warm at the end of the Triassic into the Cretaceous. At the end of the Triassic into the Jurassic into the Cretaceous, and essentially created a warm climate during most of the Mesozoic period. So the creation of the Atlantic and the Indian Oceans, caused extreme oceanic crust production, which in turn raised sea levels around the world and flooded the continents with interior seaways. So this basically is stabilizing the climate. More water, the weather, less fluctuations. Think of Siberia, which is freezing in the wintertime, but equally as hot in the summer. But then you go to England and or San Francisco, and it just the wind and the water is cold, or it's not really cold, but it's like 60. It's around 60 degrees, and it essentially stays that way year round, and it essentially regulates the climate in these areas. Not too hot, not too cold. Not to say it never happens, but it does. Higher sea level equals more water surface area, thus regulating temperatures throughout the world, and it stayed that way for the majority of the warm period of time through the second two-thirds of the Mesozoic. India is now about to move over the Reunion hotspot, and that is going to be explained. And reptiles have now become the dominant species during this time. So, and this is not a correct statement. India was making its way towards the Reunion hotspot. It wasn't didn't happen until later on. This is a time period from the end of the Triassic to basically the end of the Cretaceous. So I just want to clarify that. All right, global temperature versus oceanic production, ocean crust production. This is an interesting graph. Time is going from this way to this way, and I apologize because some graphs it does the opposite, and I'll do my best to quantify that. Anyway, green is the KT event. This right here, this is a period of intense crustal ocean crust growth, and it goes from basically the Jurassic through the Cretaceous. And you can see right here that temperatures remain very high for the majority of the period, and sea level increases over time. This is one of the most obvious things is that the more that this begins to produce, the more sea level begins to go, because of the flexing of the ocean crust erupting these rift zones. So essentially, we have an increased rate of intense ocean crust growth. We have a temperature that is just because of increased production. We have yeah, we have from the camp from the central Atlantic Magnetic Province, we have a warming of the climate that stays warm because of the amount of greenhouse gases being pushed out. Sea level is rising, flooding the interiors, giving life. Life flourishes when this happens. Um, this is petroleum reserves. We're not going to really worry about that. It doesn't really have much to do with what I've talked. But I just wanted to give you an idea of what's going on. And this is CO2. I really don't really know how to make much use of this graph. Seems as if there was a lot of CO2 in the atmosphere early on in the Paleozoic, as well as in the Cambrian. And then it drops, kind of makes a comeback right here at the extinction event, of course, because of the Siberian traps. And then it sort of stays high because we have a lot of eruptive areas. The oceans are spreading, and we're just producing a lot of CO2. So this makes sense. Lots of ocean crust being produced, pretty warm temperatures. Global temperatures over the last 500 million years. Time now is going this way. We are really cold, to be honest with you. We are down in this area, which is, this is a world of polar caps. And, the majority of the time we are actually warmer than we are now. But what's interesting here is that, very warm up until the Devonian period. Then you have a crash. And this is probably from Gondwana, the ice caps reflecting sunlight. And then you have a rapid rise of temperature for whatever reason. About 300, about what, 275? What would be causing that? I'm not sure. In any case, there is a rapid rise of sea level. Of temperatures, and then of course there's a crash right after, and then we kind of bottom out, and then all of a sudden temperatures start coming back again. Again, probably related to the opening of the Atlantic Ocean right here and the increased oceanic crust production, and we peak here in the later, kind of mid to late Cretaceous, and then we start to drop, and then right around the extinction event, things just go nuts. As you can see right here. So when you have fluctuations like this in a short period of time, that usually doesn't bode well for life. And here we've been in a continual trend. Climate's been cooling. Probably has a lot to do with Antarctica moving over the pole, and then down here we bottom out. This was the last ice age, but now we've been spiking very quickly, and this is mostly due to our climate change of from CO2 being released, from fossil fuels. Why this occurred, I have to think. I don't know why that happened. Why that's there. I know that this has to do with going into somewhat of an ice age, and probably Gondwana coming together. What was happening at 275 million years ago? I don't know. But this heated up. Probably Pangea being on the equator is what caused this. Probably brought us right out of that. Yeah, that's where I'm going to go. Pangea being right on the equator. Temperatures would definitely start to rise. In fact, this rapid temperature rise I do talk about in my Permian extinction talk, and this makes sense right here. Why was that happening? That was happening. I don't know, but I'd have to go back and look at my research on that. Why that happened. Think. Pangea came together. Pangea was on the equator, a big part of it. Mountains were mountains were sucking up a lot of the CO2. Um, so maybe this is the mountains eroding, and now CO2 is starting to get pumped into. That's what it is. Yeah, this is Pangea leveling out, and the CO2 sink is not there, so temperatures start to rise. All right, so that accounts for that. Almost confused myself. All right, sea level change related to supercontinent cycle. So this is an advanced chart, but the gist of it is we have an ocean was growing back 540 million years. This basically is relating to Pangea's formation, and most in particularly on the east coast of the North America. So in the Cambrian, we had the rifting of slices of Africa, northwestern Africa, that kept getting ripped off because subduction zones formed off the coast there and migrated over towards near the coast of Africa, and just due to subduction began to tear off pieces of Africa and then make it travel across the Atlantic Ocean. And this is the opening of one such piece of strip of coming off Northwest Africa called Avalonia. And once Avalonia rifted off of Africa, you had an ocean, and that's called the Rheic Ocean. And then the Rheic Ocean started moving across as Avalonia started moving across the ocean, and encountered island arcs and what have you. And at some point, the Rheic Ocean began, subduction started in the Rheic Ocean, and it began to close, kind of like a Wilson cycle, an opening and then a closing, and it closed all the way down until Pangea comes together in the Carboniferous. And this is indicative, is that so when you have rifting, sea level is high. When you have closure, sea level comes down, and when you have rifting, sea level is high, and then sea levels has been dropping since the peak in the Cretaceous. Basically, probably represent. I mean, it takes more than a few things to just drop a sea level. It's a few things, but generally glaciations, which we went into a glaciation in the last 60 million years numerous times, and that has and obviously Greenland and Antarctica have ice caps, and this is probably what has caused this downdrop, because Pangea is still the oceans are still spreading, although the Pacific is closing. So this is just saying that when you have a widening, when you have oceans basins being formed, you have a tendency for sea level to be high, as indicative here, and when you have subduction and oceans closing, you tend to have sea level go low. And that we may have had a decrease in production. I'd have to go back and look at one of my charts. Let's see here. Yes, production rate did stop. So this is ocean production did stop. So whenever you have ocean crust production stop, you have drops in sea level. Okay, good. All right, so worldwide hotspots. Each one of these dots represents a hotspot, and the hotspots can either be they don't really care if you're in the ocean, if you're on ocean crust, or if you have a continental crust above you. It does not seem to care. They will punch through just about anything. So what we have is Yellowstone is a classic example of a continental hotspot. Iceland and Hawaii are oceanic hotspots. Most islands that seem to randomly pop up in the middle of the ocean are hotspots. Even Bermuda was once a hotspot. We even have one in New England that basically started in Quebec, and as the North American plate moved over, it ended up creating a massive volcanic epicenters in New Hampshire, some in Maine, and then off the coast here, and then right across the Atlantic Ocean towards the mid-ocean ridge, and even continuing on the other side now, which means that the ridge even itself is progressing westward. So these things are numerous. There are a lot of places, and they are just areas where the mantle wants to punch through and come through to the ocean or the continental surface. And the one that we are concerned with is this one right here, the Reunion hotspot. And there is India right now, but at some point in the last 60 million years, this thing went right across this and it covered most of it with lava. So 94 million years ago, here is the Cretaceous global view. We have the Reunion hotspot. We have India, and it started. The subduction has now started over here under the Southeast Asia or the Eurasian subcontinent. The ocean, known as the Tethys Ocean, is now closing, and the Indian actually is being born right here. This is going to be the Indian Ocean, and this is getting pulled very rapidly across over to crash into Eurasia and make the Himalayas. So eventually it's going to go in the next 20 million years, it's going to go from here, and it's going to go right over this, and it is going to just cause massive volcanic eruptions. And as you can see, there are interior seaways in Africa, South America, Asia, Europe, and North America, and this is helping regulate the climate. That's the impact area, which is not going to happen for a while. Now we go to 70 million years. Impact areas still, water. There's still some seaways, but not as much. The continents are starting to dry out. India is now about to go over the Reunion hotspot. And 75 million years ago, we were looking at North America. We have a beautiful seaway right here. Lots of lice, tyrannosaurs, triceratops battling it out. Duckbills. I mean, just as good as you could get for life. It's warm. The equator's kind of down here somewhere. The continent as a whole is further south. You got some highlands here. You got the Rockies starting to really, make their statement. And of course, this is where the Yucatan, a future impact site, is going to be. This is keeping weather nice. This is keeping animals happy, and life is thriving. Again, another chart of oceanic crust production and sea level. And this is telling you a few more things here. So, Triassic extinction event for the Triassic into the Jurassic. Jurassic right here. We have numerous flood basalts occurring, not just the Deccan, but this is crust production just really cranking in the Cretaceous, and of course sea levels are following suit. So these carbon isotopes, they have a tendency to tell you when life is thriving and when it is not. And as you can see here, there's a huge dip right here. That means that there's not a lot of biocarbon carbon dioxide being produced, and then life comes back, and and then we don't get there because it stops. But this is a huge drop right here during the extinction event. And also, these are ocean anoxic events. This is what happens when you have too much CO2 in the ocean, and it becomes kind of stagnant, and life just doesn't do very well. But they're not really important to our talk right now. This is just, I wanted to show another relation to sea levels and crust production. And these are the amounts that have been produced, and like this was just a huge one, and that likely resulted in in the warming of the climate, like I said, through most of the Cretaceous, through the Mesozoic. This did not necessarily rise sea level because it was creating a new ocean basin. So it didn't influence it that much. It happened more later when you have water over it. There just wasn't water here yet. Cretaceous Tertiary, 65 million years ago now. Now we're getting, this is where when it happens. This is the impact event. It's going to be right here. Oh, that's just where we live. For some reason I always label that. Interior seaways were removed, and now temperatures are starting to fluctuate. All this area right here, this giant swamp, and this is on other continents too, is gone. So anything that lived there is dead. Anything that ate the things that lived there is dead, or they had to adapt. And now, what was once a tropical, somewhat just consistent paradise is a dry area, and that's causing a lot of problems. It's stressing the life forms that live there. So now the event. Oceanic crust production begins to wane, lowering sea levels worldwide, draining seaways off the continents, and exposing new land, thus stressing many of the species that lived in those locations, i.e. life forms are stressed. Interior seaway allowed temperature to fluctuate. The lack of an interior seaway allowed temperatures to start to fluctuate much more radically on land and eventually in the sea due to the draining and the mixing and the cooling of seawater. The lack of volcanic activity, CO2, further enhanced the cooling of the climate. Prior to we're coming up to the extinction event, volcanic activity did wane, and that's why you have that peak in the Cretaceous, and then it begins to wane. India has now moved over the Reunion hotspot and started a major volcanic event, the Deccan Traps, which affecting the Earth. Slowly at first, but then increasing, eventually producing enough lava to bury California 2 kilometers deep, or the U.S. 200 feet thick. The initial release of SO2 and CO2 reflects sunlight, and then the ratio of those reflects sunlight. When you get more CO2, it reflects the sunlight, and then causes major climate fluctuations, because then when the CO2 comes back, it starts to warm. Right? So you're cold, hot, cold, hot, cold, hot. All right, so the Deccan Traps in India. These are them. They probably occupied an area much bigger than that, probably somewhere out here, underwater. As you can see, they're very flat, very level. They have not moved since their eruption. Hence, India's not been crunched in this area since then. It's been driving into the Himalayas, but it has not been. This part has not been affected. And like I said, these are over a mile thick. There's this unfathomable amount of basalt, and individual flows, I believe, are the biggest that have ever been measured. Talking like, some of them just cover thousands of miles. Another map showing India traps, and again, I'm gonna go there probably, or something like that. All right, Deccan Traps are a large igneous province, a lip located on the Indian subcontinent peninsula. They produce some of the largest known lava flows, covering an area the size of India, with the bulk of the mass extruded over a mile deep. They are thought to have been initiated by India removing over the Reunion hotspot, 66.5 million years. The release of volcanic gases, particularly sulfur dioxide, during formation to the traps may have contributed to climate change. An average drop in temperature of 3.6 degrees Fahrenheit or 2 degrees C was recorded during this period. Although it had started to prior to the Chicxulub impact, eruption rates appear to have increased 8 to 10 times on an order of magnitude, very close and after the dates of the Chicxulub event. So this is where these things kind of seem to interact. We think that the traps may have been agitated by the impact event, because when you hit something of that much power, you have a tendency to affect the world globally. And by affect it, I mean shaking it vigorously. And I'm going to get into that, I think, right after this. Um, so, this is the traps cross-section, the location. This is sort of a cross-section of what we're looking at. And you can see that you had um, sort of small-scale eruptions, and then, you ended up making about half, a little less than half of the amount of traps. Um, but then, eruption rates begin to pick up, and you have just absolutely massive, two massive eruptions after the initial impact, and these are the ones that really seem to just cause. I mean, you were causing problems here, but to have this much come out, right after you've already just had a huge blowout right here, and then you have two more on top of what this did. I mean, it just decimated everything. Mass extinctions with a correlation to lips and terrestrial impacts. This is an interesting graph. So we have this one right here, and this one really doesn't seem to have anything related to it as far as a lip goes. However, it does have small craters. There's a sort of a flurry of them right there. So for whatever reason, possibly that had something to do with it. I don't know. But something went on. There's really no lip associated with it, so we're going to go, maybe there are some impacts here, because you do have some iridium. Microtectites, we do not have any of those. I have to look that up. I think I know what that is, but I'm not sure. Okay, so here's so this would be indicative of an impact. Okay, sure. That's where you're going to get the iridium. Okay, so Devonian one right here. Yep, got a big one right here. 300 to 370. Yeah, that's right over there, because it's 360, I think, is when that happened, or right around there, a little later. You got some impacts right here, and you have both iridium and microtectites. So possibly a combo effect here. You have the big one, the KT. The KT, I mean, not the KT, the PT rather, the Permian Triassic. You got Siberian traps, and then you got something else over here, which doesn't seem to have a name. In any case, the traps are, these could be traps too. This is just one of the biggest on Earth, and there is no iridium and no, so we're going to rule out an extraterrestrial problem. This is probably just the traps, or climate change leading up to it. The Jurassic one, we got a lip right here. We got the Camp 2, so you got a couple of those. You do have a little bit of iridium here, but really no impacts to speak of. And then you have the KT one, big old lip right here. You've got some underwater ones here. Then, of course, you've got the impact right here. So you've got definitely iridium and microtectites. And I apologize, I need to figure out what those have to do with whether or not what they actually mean. Microtectites. I'm gonna write that down. I'll get back. Microtectites. All right. This is the trap volcanism and related mercury found in soil. So that when the traps erupted, they put in a ton of dust, a ton of dust in the air, and in that, when these erupt, the volcanoes produce all sorts of little toxins and metals and everything. But one in particular is mercury. And sure enough, this is sort of the traps over the, from 66.3 to 66.03, I don't know, 66.016. Okay, so you got about a 350,000 year period here, right? Yeah, 350,000. And in that time, you have eruptions coming out here, and the volume of it starts off right around here at 66.3, and then really just starts to pick up, and then it just absolutely cranks. And it's interesting how the impact event pretty much precedes the uptick in volume. So it's pretty safe to say that there's a possibility that these things could be related, because there's the volume just spikes, and of course, once all this gets into the air, you have this gigantic spike in mercury. And you can see it's sort of a delayed effect. You get kind of a bunch here, and all right, then it shows up. For some reason, this doesn't seem to be correlated with anything. This here, and then it kind of peaks here. And then you just have this unbelievable spike. And mercury is not good for anybody or anything. And then, more so, you kind of look at at what you're seeing for deposits. Sands and marl, that's either near shore or it could be desert, it could be whatever. But when you get into shale and clays, you have a wet, very calm environment. So right after the impact, you had some marl, and then you went into just all of a sudden this must have been from all the ash falling out, and then you're in a shale situation. So again, a huge change in facies right here, right at the extinction event. So anyway, interesting chart. Boom. No explanation needed. I think that is pretty self-explanatory. So yes, we have an impact, and how do we know that happened? How do we know that this occurred? Well, there's a variety of reasons. One, there's a hole that we see through seismic profiling. Two, there's a layer of dust that contains high levels of uranium pretty much around the world that gradually gets thinner as you move away from this particular area, and thickens when you get there. And it looks kind of like this, just depending where you are. You've got the Cretaceous marl here, and then this is basically saying that you have this is an active, this is being produced by calcium precipitation, which means living things, shells, what have you, and then you have dark shales up here, which basically means your life is not really doing very well, and in between you've got this dust of this layer of iridium. And iridium is mostly found, it's primarily found in extraterrestrial bodies, because they are primitive as long as they aren't differentiated. Once your planet differentiates, heavy elements go to the center. That's why most of our iridium is in the center of the Earth. It's not even in the mantle, so the volcanoes are not capable of producing this. So it has to be pretty much for certain an extraterrestrial source. So, I mean, there's trace elements of iridium, of course, and everything, but then you have this gigantic spike, and then it's back to normal. So, most likely a terrestrial source in an impact event. This is just a more sort of crazy diagram of it, but this is the boundary, KT boundary. Right here is again the layer of iridium, smectite. And then you've got coal here, which is, this is a thriving carbonate swamp. And then you have sort of a change in it here, where it's as if it's not nearly as dark. It's hard to really tell if how much carbon is really in that. And then you go to a mudstone, which is just basically there's not much in there. It's very light. All right, Chicxulub Impact, 66.051 MA, a 6 to 9 mile metallic rock impacts the Earth near present-day Yucatan Peninsula, puncturing a hole, through the Earth's crust over 20 miles deep. It did not go into the mantle. That is, I got to take that out. It punched and it affected probably the mantle, but it did not. I don't believe it punched through it, and almost 200 kilometers wide. The impact has the following repercussions: a 11 magnitude earthquake. I mean, that just essentially says that it's bigger than what we can really conceivably think of, but really you're just dealing with a 9.0 essentially felt worldwide. To put it in perspective, I can only imagine that if you think of an earthquake, initially it's just the rupture. It's just displacement in the crust. So if something ruptures, it will jolt. And when it jolts, in generally less than a second. So, you think of a, 5 magnitude. Maybe an area underneath you jolted. I don't know. I mean, I'm just making this up, but I mean, maybe it jolted 4 or 5 inches. So you move 4 or 5 inches underground in less than a second. All right, boom. That's actually quite a bit. Maybe it's less than an inch. But let's just say you have an 8.0 or 9.0, like happened off of India. I mean, not India, Indonesia or Japan. And we know that the slip was in the order of a meter or two in less than a second. So if you're standing there in a house and you moved a meter or two in less than a second, you're going to be just smashed into whatever wall that's within a meter. If you're not, you're just going to get you're going to be jolted a meter across the room. And something that, like an impact like that, I mean, I could imagine moving 6 feet. I don't know. I mean, but if you move in less than a second, you are smashed into whatever is less than 6 feet around you. And that goes for animals in the woods, human beings. I mean, we weren't around, but any life would have been just immediately moved, which in turn causes snap trees, avalanches, things to collapse, caves, burrows, whatever. Then you got to think of every water body is being sea-shaped like a tub. You just start rocking back and forth, and the water is going to move in the rivers. Something like the Mississippi, depending on the direction of impact. Wherever it's perpendicular to the direction of the force, the wave, force of the wave, you're going to be sea-shaying in and out of the banks. And Great Lakes, not big lakes, Great Lakes, oceans, all of them are going to just be making up for this gigantic displacement of water. So, not to mention the nearly 1,000 foot wave generated in the Gulf of Mexico from this, which loses its height quickly, but still, you're looking at 30, 40 meter, or who knows. I mean, at least in the Atlantic, it certainly bent around and shot the gap of Cuba and or whatever. Cuba may not even been there, but in any case, it definitely blew out through there and into the Atlantic, and then circumnavigated the world's oceans. What it did to North America, I mean, we're talking hundreds of miles of inland run-ups. So everything dead in its path. Um, Most species, I'm sorry, so 60 days of total darkness, maybe give or take. That's just a guess. I'm sort of in the middle. Some people think less, some people think much more. Let's just say minimal. Most species within 1,000 miles are immediately burned within minutes. Others take longer, but most meet the same fate. Tsunami affects all ocean, but the Gulf of Mexico likely saw wave heights over 1,000 feet and slammed into the U.S. in less than 2 hours. Later, running hundreds of miles inland, killing about everything in its path. And then the 11.0 magnitude earthquake agitates most of the world's crust, possibly causing a massive increase in worldwide volcanism. And most importantly in India, which is almost directly on the other side of the impact site. Now, that is a statement I'm using very loosely. It is not at the actual convergence point. It is, however, on the other side. And, I cannot possibly believe that, given the imperfections and in the crust, the different densities and everything, that the P and S waves, perfectly aligned up and converged on the absolute dot of the other side of the world. I'm sure that they affected different areas differently. I'm sure that other places that you wouldn't even think of were rattled way more than places than you think. I mean, I've seen tsunamis in the Pacific Ocean show up at the strangest places, and I'm sure that because it's a shock wave, it would do the same thing. So who's to say it didn't do some weird things on the particular continent of India and over the hotspot? But in any case, it certainly shook it up. And you shake up a Coke, a champagne bottle, that cork comes out a hell of a lot easier. And I have no reason to doubt that this would be any different. So if you have a subcontinent over a gigantic hotspot that's just really trying to get out and it's punching through here and there, but then all of a sudden you shake the hell out of it, well, and pop the cap, it might just be what you needed to make that thing go ballistic. And that seems to be the case, and I'm sticking with it. Chicxulub impact continue. The dust produced released massive amounts of toxins into the air, causing acid rain and eventually acidification of the oceans, and no reef production and no removal of CO2. It also released a massive amount of mercury and iridium, which only found at the Earth's core. It coincidentally formed bodies like comets and asteroids. It caused an immediate rapid cooling of the climate due to the SO2 dust, which likely hollowed photosynthesis for months, maybe years, followed by rapid warming due to CO2 and increased volcanism. Chicxulub Crater. This is sort of the outline of it. This is what it looks like on land. It kind of, half of it's on land, half of it's out in the water. These sinkholes seem to correlate right with the boundary of the rim of the crater. For reasons I'm not 100% sure why, but I do believe it has something to do with the shock of the minerals, the limestone here, faulting maybe. But whatever the case is, there's definitely sinkholes have formed and they make a conspicuous ring around here. So for whatever reason, there's a weak point there. So this is what happened. T-0, nothing. Everything's peaceful and wonderful. T-1 minute, the thing hits. You've got melting at the bottom. You've got pulverization of everything. Close to within 180 miles maybe. The crust is actually getting flipped over. All the water is getting blasted out. 3 minutes, you've got the peak in the middle, the center peak, from all the materials getting bounced and then popping back up. And again, you do have a little bit of mantle flexure here. Now you've got gigantic faults and cracks and everything, and all this melted rock up here is erupting and causing volcanoes. This is 30 minutes after the tsunamis are coming back in and filling and boiling. There's breccia coming down. After an hour, the ocean has now resurged in and out, and maybe quelled some of these eruptions here. A matter of hours, you've basically got a whole layer of dust and stuff on the bottom. You've got magma on the bottom that needs to basically starts to harden. The crust is all warped. It is bent. It is shocked. And then in the first day, everything is everything is sort of calmed down. You're going to have a rim maybe form from sediments washing back and forth in and out of the crater. Hard to say, but within a day you're going to have things will have settled somewhat, but you're going to have a reservoir of molten material in the center that's cooling. You're going to have a rim from the back and forth, the seashaying of all the materials coming in and out, plus the extent of where it actually blew out a hole. So you've got a mess, and it's going to take years for this to clean up. Now today it's completely filled. You barely can even notice it. There is a conspicuous little dent in this mountain right here, but other than that, you wouldn't even know it's there unless you did seismic profiling. How do we know it's there? Well, from seismic profiling, and these are gravity readings, you can see it really perfectly right there. This is the old shoreline, by the way. I mean, the shoreline of today, and again, there's that mountain right there. And that mountain's popped up because it's hardened. So it's a resistant peak. The center ring almost looks like it's inside, or right on the line of the shoreline there, and you can see the deep, the rings, the center peak. You can see what looks like maybe, I forget what they call this. There's a name for it. Oh yeah, the tail. It could be that this thing came in and there was a it was oblong and it just hit this first, and then this is the actual impact. But we think it came from this direction here. This right here is also showing rings, sort of a peak in here. You can also see a ring here from the actual tail or whatever it hit right there. And these are the sinkholes and everything that formed around it. But yeah, it does show up seismically, without a doubt. I'm attributing this cold. This is dense, so this is basically makes a very heavy center. Wherever it hit, it compacts and make things dense. Not to mention stuff filling back in. Anyway, blast radius. I don't know what this is, but okay, so that's 1,000. So 1,000. 2,000 kilometers, you're pretty much dead. Hurricane force winds, boiling temperatures. This. I'm just guessing, but anything in here is that's it. You're vaporized. Impact events within 24 hours. You get one impact. You hit the carbonate platform, everything gets pretty much melted, blasted into the air, pulverized. Then you have a outward going tsunami in 0 to 24 hours. I mean, they're going to be going back and forth, but you're going to have tsunamis running around for at least a couple days. Debris, it's pushed into the air. And then the impact crater has, these melt sheets inside of it from everything that was molten. So, a mess. Impact summary. These are sort of the results. Plain language summary at the end of the Cretaceous about 66 million years ago. The Chicxulub asteroid impact near the Yucatan Peninsula produced a global tsunami 30,000 times more powerful than any modern day tsunami produced by today's earthquake. So, I mean, 30,000 times bigger than, the Indian Ocean or the Japanese one. I can't even imagine what that would do. Well, in any case, so these are sort of the timeline of events. The media events are fireball, air blast, earthquake, tsunami, and basically you're just burned to death and buried. That's local and regional. Um, within a few months, you're still dealing with fire, soot cooling, pyrotoxins, and acid rain. Um, as well as you don't have any photosynthesis, and you have, there's you can't see shit. Um, so, and then, for years you're looking at cooling. Still, probably acid rain is going to continue for months again. But now you're looking at ozone loss and cooling of the planet for a couple of years. Um, SO2 is causing acid rain and cooling for years, adding to that. And then heavy metal poisoning for years, and then now you've got a long warming trend coming up for decades. So, up and down. On top of what the Deccan Traps are doing, which are contributing their own ups and downs. All right. This will be the last part of section 2. Part 2, rather. So the Deccan Traps, they initially erupt slow, but enough to cool and then heat the climate. Oceanic crust production wanes, and sea level drops, exposing continental interior seaways and shelves, also allowing more extreme temperature weather fluctuations. Drop in sea level also stresses out species that live there and those that feed on them. Traps are progressively releasing toxins, mercury into the atmosphere. That's not good. Impact event occurs, blocking out sun. 9 to 11 magnitude earthquake creates massive tsunami worldwide, generates a 9.0 earthquake worldwide, triggering volcanism worldwide, possibly causing the Deccan Traps to erupt a magnitude or 8 to 10 times the previous rate. Massive temperature fluctuations in a short period of time, basically exponentially accelerate, or they begin to in what's the word I'm looking for? The temperature fluctuations were already a problem, but once you have the impact event plus the increase in Deccan Traps volcanism, it's safe to say that the temperature fluctuations increased tenfold, and that occurring on an already stressed out environment is going to prove to be, an extinction level event. Volcanism also acidifies the oceans and may contribute to the anoxia of water bodies, as evidenced by the dark shales found around the world. Dark shale is basically saying you don't have a lot of stuff living there. And then primary food sources are wiped, resulting in worldwide famine. Other things to consider: possible massive increase of lava in India, flexed crust, and may be related to vertical cracks in lavas older than impact, but don't show up after. Sea level drop later in Cretaceous, no seaways as the camp output decreased, lowering oceanic crust, which makes climate more susceptible to temperature extremes, which stresses nearshore organisms and their food sources. So, on top of everything, remember, if in fact we had a huge increase in the eruptive rates under India, it is possible that it could have actually lifted the continent, and maybe even it shows up in some faulting of the lavas previous to it. And then also, again, that later drop in sea level in the Cretaceous, taking away the oceanic seaways, caused major extremes in weather and storms. So it's making everything more susceptible. And that will be the end of part 2. Thank you.